Hello, my name is Yannick Broschart. I am the co-author of Professor Wolfgang Kurz, and now I will have our presentation on development of a new design approach for composite dowels positioned close to the concrete surface. This graphic shows different types of positions close to the free concrete surface. It can either occur when the composite dowel is positioned very close to the edge of a concrete slab, or if the composite dowels are arranged horizontally. Especially for horizontally arranged composite dowels, the slab thickness can then be set very small and even underneath the current limit from the German approval, which is set to 250 millimeters. The typical failure mode that occurs for those positions is the so-called edge failure, which looks like this, and the concrete cover next to the composite dowel spells. We then had push-out tests to investigate this very failure mode, as you can see them right here in small scale tests, and they had the very same failure. We used different measuring techniques to investigate the performance of the composite dowels, such as a 3D measuring system, which consists of a stereo camera system and a projector. With the stereo camera, we took single shots from different perspectives from the steel part of the push-out specimen. And these single shots were triangulated to a full body model. We performed such a scan before and after the push-out test, and by overlapping those two scans, we could focus on the deformation of the steel tee. We furthermore used conventional measuring techniques such as inductive displacement transducers to focus on the one hand side on the slip of the composite dowel and on the other hand side to measure the thickness variation of the concrete slabs. The total experimental program consisted of 32 push-out tests with varying parameters such as the concrete strength, the position of the composite dowels, the concrete slab thickness, the steel plate thickness, the dowel geometry, as you can see it right here, the size and center distance of the steel tee, and the depth of the embedment, and the position of the reinforcement stirrup. The marked parameters are the ones that I will focus on with the following slides. At first, the influence of the concrete strength. We had different push-out tests with concrete strength C20-25, C40-50, and C60-75. It's not very extraordinary to see that with higher concrete strength, the total load-bearing capacity also increases, as to be seen here in the load-slip diagram. But what is very extraordinary to see is when you focus on the relative displacement and how it can be divided into a part that comes from the steel deformation. This is what was measured by the 3D scanner, and the rest of the relative displacement then must come from concrete deformation, which is this part. So you can clearly see that the weaker the concrete is, the more of the relative displacement comes from concrete deformation instead of steel deformation. This effect is also the basis of our design approach, which I will show you later on. But to have a little spoiler right here, I will show you this picture, which shows that right in front of the steel tooth, the concrete is set into a hydrostatic compression stress state, and at some level of force, this concrete right here, it starts to pulverize. This pulverized concrete is then pushed aside and allows the steel tooth to slip right through without high deformation of the steel tooth itself. So the deformation comes from the concrete deformation. This slide shows the steel teeth deformation to prove the former mentioned effect. And it clearly shows that for higher concrete strengths, we can see with our own eyes that the steel teeth are deformed to some extent. When you look on the contrast to the steel tooth deformation for weaker concretes, you can see that the steel teeth aren't deformed very much. So the total relative displacement that we clearly measured, it must have come from the concrete deformation. Second of all, I will show you the influence of the width of the concrete sections. Our standard configuration had a concrete width of 100 millimeters, which was then increased to 150 and then to 200 millimeters. What the load slip diagram shows is that to a certain load level of round about 265 kilonewtons, the load slip behavior is pretty equal, but then it starts to develop very differently. The explanation to this behavior can be given by two effects. One effect is the pulverization of the concrete that I mentioned before, and a second effect that overlaps right here is the plasticization of the steel teeth. This can also be seen here in the splitting up of the relative displacement. Since for small concrete slabs, the total relative displacement mainly consists from the concrete deformation. Especially for higher slab thicknesses, it mostly consists of steel deformation. This can also be seen when we focus here on the deformation measured by the 3D scanner, where there are high steel tooth deformation in combination with high slab thicknesses and smaller steel deformation corresponding to smaller slab thicknesses. The third and last influence that I want to show you today is the one of the reinforcement stirrup position. In our standard configuration, we had 2 reinforcement stirrups per gap between 2 steel teeth. The upper reinforcement stirrup was called the load-facing stirrup, and then there's a second stirrup underneath this first one. As I said before, this is the standard configuration. Then we changed the configuration by taking away this second stirrup, which used to be underneath there. And it can be seen that the load-bearing capacity decreases only to a little extent. What is really interesting to see is what happens when you take this last remaining stirrup per one gap and instead of positioning it right underneath the steel teeth, we positioned it in the middle between 2 steel teeth, so in the middle of this gap. And what happened then was that the load decreased by around about 1/3. On the basis of all the investigation results that I showed you before, we then considered on how the load transfer mechanisms must look like. First of all, what I mentioned before, we are very sure that right in front of the steel tooth, the concrete starts to pulverize and is pushed aside. We are very sure about this because otherwise you could not explain the high relative displacement that we measured in some cases without a corresponding deformation of the steel tooth. That's what the 3D measurements showed us. This also corresponds with a very first crack area right in the center of the concrete slab, which cannot be seen from outside, and which does not have any strong impact on the total load-bearing behavior, because this crack area is crossed by a reinforcement stirrup. The second crack area, which happens to occur right-angled to the first crack area, is the first one that you can see from outside, and it also does not have any strong impact. What then finally limits the total load-bearing capacity is the third and last crack area, which occurs right underneath the reinforcement stirrup. And the explanation for this failure mode is that as long as there's concrete underneath this hydrostatic compression stress area, then the pulver can be pushed aside and even downwards to some extent, but the pressure level in this area, it still can be kept up high. Only if the concrete spells underneath the reinforcement stirrup, then the concrete pulver, it can like flow away downwards, and this is what limits the load-bearing capacity. On the basis of these considerations, we then developed a design approach, which is summed up very shortly here on this slide. And since time is not very much today, I would like to ask you to look up in our full paper if you are interested more detailed in this development of the design approach. We also performed large-sized beam tests to check the transferability to structural components. And we could validate the design approach with the help of these tests, which also showed the same failure mode, edge failure. Then this is what the final design approach looks like and what parameters it consists of. Our medium-term goal is to have the design approach published within CEN-TS, a technical specification, and the long-term goal is to have it integrated into Eurocode 4. Thank you very much for your attention. These are our references.